Okay, this is the second hour of Physics 1C for 1B, excuse me, section 1376 for September 20th. And we just discussed how two objects can have the same temperature. And now we are going to talk about thermometers and temperature scales. Why is that not working right now? All right, well, a thermometer, as you all probably already know, is a device that is used to measure temperature. And we have different ways of going about doing this. The simplest way that you can construct a thermometer is by taking advantage of the fact that things tend to expand when they are heated. Is that something that you all are aware of? Is it most or all? Don't know. Most fluids, solids, gases, whatever. Most fluids and solids expand when temperature increases. This is not taking into account of phase changes, like when water cools from being liquid water into ice. Ice is a higher volume than it would have been in liquid water form. So this is as long as it stays in the same state. Most fluids and solids expand when temperature increases. So as a result, one of the easiest things you can do to construct a thermometer is you can take a vessel and you can fill it with common fluid like water. So we have water in here. And then inside of the vessel, what you do is you place a glass that has alcohol or mercury embedded within the glass itself. And there's like a column along which it can travel. So this would be the most common type of thermometer. You've got some well at the bottom of a fluid, usually like mercury or alcohol is the most common thing. And when it's alcohol, I think it's dyed red commonly. And so you've got some pool of this fluid down here, and you have an open capillary along the tube itself that allows the fluid to rise, right? And so what you do is you go through a couple of diagnostics to set it up, I guess. You say, suppose that I take this water and I fill it with ice. So I put a bunch of ice in here. So each of these are ice cubes. And I let the water, give it some time so that it comes into thermal equilibrium with the ice. Then what we'll have is ice water. And if we go and we mark off on our scale exactly where the ice water, where the alcohol rises to, then we can label that to be, what's the freezing point of water in the Fahrenheit scale? Does anyone know? 32 degrees, right? So you could label that this is 32 degrees if I want to use Fahrenheit. Or in Celsius, that would be 0 degrees Celsius, right? Put a mark, right? Just label it on your thing. Make a very strong mark on there. Maybe use a different color to indicate what markings we're making. So you put a marking on there and you say, okay, that represents 0 degrees Celsius, right? And then you take your same system, right? And now you remove all the ice. So we get rid of all the ice. Now we're going to heat it up until it's boiling, just on the verge of boiling, or boiling. So we're going to have now boiling water. So now it's, there's steam coming off the top of it, right? And now what's going to happen is that our scale is going to rise higher. So the liquid in here expands. But it can really only, when it expands, it can really just only kind of go higher. And then we mark off exactly what that one is. And then we say, okay, well, that has to be, let's start off with Celsius, because I'm sure you guys all know the answer to this. What's the boiling point of water in Celsius? Everyone knows what that is, right? 100 degrees Celsius, yeah. So you say this is 100 degrees Celsius. Now here's the other one that I don't think everyone always knows. What's the boiling point of water in Fahrenheit? We're all very used to Fahrenheit, but I don't think everybody always knows the answer to this. Do you all know? What's the boiling point of water in Fahrenheit? No, that's not right. Good guess. 212, that's right. Did you have to look it up or did you know it? Be honest. Oh, you did the calculation with this one, huh? Okay, that's fine. That's just as good. All right, so 212, that's correct. Yeah, this is, your kettle goes to 212, it makes sense, yeah. That does make sense. So this is the conversion factor right here between Fahrenheit temperature and Celsius temperature if you want to use it. It's a very strange conversion factor, but you know, it has this plus 32 here because the Celsius scale is, 0 is 32 basically for the Fahrenheit scale. Okay, so now once you've done that, what do you need to do to be able to measure other things? Well, it's really easy. You just take your thermometer. You already know. Let's pretend we're trying to calibrate a Celsius thermometer. Okay, so over a large enough, over this kind of small region from 0 degrees Celsius to 100 degrees Celsius, the alcohol that's in here is going to expand in a linear way. And what that means is if I come right to the middle, we've already indicated that this was 0, right? 0 degrees Celsius, and this is 100 degrees Celsius. And you all know that the Celsius scale, maybe you do, maybe you don't, I don't know. It's an evenly divided scale, right? So if I come here right in the middle, that has to be 50, right? And if I cut it in half again, it has to be 75. Because like I'm saying, the expansion of this fluid inside of here is going to be a linear expansion. And then you could just, you can create as many marks on here as you want to, right? You could technically make something like this yourself if you could go find an unlabeled type of thermometer like this. But that's how we construct a thermometer, right? We take reference points, like we decide that ice water is going to have a freezing point of 0 degrees Celsius, boiling water is going to have a boiling point of 100 degrees Celsius, and then you just, mark off the rest of them, and that'll give you your temperature scale. Now, this temperature scale is pretty good. It does have one problem, which is that the temperature can become negative. And it's not like that's really a problem. It's fine to have negative temperatures, right? It's perfectly fine to have negative temperatures. On the Celsius scale, negative temperatures are very common. On the Fahrenheit scale, it has to get really, really, really cold outside for it to go into the negatives. Have you ever been outside, like in a cold area, like maybe on, I don't know, you've gone to visit friends that live in a different state, or you've been to a mountain? Have you ever been outside when it's like negative in the Fahrenheits, when it's like, let's say, like negative 10 degrees Fahrenheit? Has anyone here experienced that? I know Southern California is basically the same temperature constantly, but this is really, really cold. Where I lived in Oklahoma, it would, on occasion, get into the negatives, and it was really, really painful. And Oklahoma isn't even as bad as it gets if you go to places like Maine, Chicago, places that are farther north, anywhere in Canada. You can get deep into the negative temperatures, and oh my god, it is so cold. It is ridiculous. I mean, even when it's only 10 degrees Fahrenheit outside, it is insanely cold. It's like so cold that you don't want to have any extremity, you want to have like a face mask on, so that the only thing that's not covered is maybe your eyes, and then you probably want to wear some sunglasses to cover your eyes. And then anything like your lips or your fingers that touch the air, you can really feel it. It's super cold. But, negative temperatures are fine. It just means that you're below a certain point, right? That's right, Troy. That's exactly what you have to do. You have to wake up and turn the car on to leave it running for like 15 minutes. You go back inside, maybe take a shower or something, get ready, and then come back out. And now the car's nice and warm and all the ice is melted. That's what you have to do when it gets that cold outside. Really, when it just gets down to 0 degrees. Like, your entire windshield will freeze over. This never happens in LA, right? This never happens. You never wake up and you go to your car and the car is just frozen over, right? It's impossible. It just never happens, right? It happens every single day in colder states that you have to do what Troy says. You have to get the car running. And you also have to get the car running just so it's hot when you get inside. So it's warm for however long your drive is, right? All right, so this is how you convert from Celsius to Fahrenheit. It's a very simple equation. I'm not going to go through an example. I'm quite confident that you all can use this equation, right? But one thing that's interesting about these scales, both Fahrenheit and Celsius, like I was saying, is they have a negative section. You can have negative temperature. And while that's fine in terms of describing how cold or hot something is, because you're just, you can understand what a degree means, when it comes to describing colder and colder and colder temperatures, And when it comes to doing mathematics, this is the important part. When you want to do math with temperature, we need another scale. So the other scale that we use beyond just Celsius and Kelvin is the Kelvin scale. Okay, and the Kelvin scale, we can write down a relationship as well. So the Kelvin is what we call an absolute temperature scale. This is the SI unit of temperature. And on the Kelvin scale, temperature in Kelvin is equal to temperature in Celsius plus, I think it's 273.15. So you take the temperature in Celsius and you add this much to it, which means that 0 degrees Celsius corresponds to 273.15 Kelvin. And when we write Kelvin temperature, we don't put the degree symbol here or here. You just put K, capital K for Kelvin, all right? It's named after a person whose name was Lord Kelvin. He was heavily instrumental in some of the developments of our understanding of thermodynamics, and thus the reason why we give him this name. He may have been more specifically involved in this, but we named the scale after him. Now, the Kelvin scale has the same, what's the word for it? A degree Kelvin, 1 degree Kelvin, is the same thing as 1 degree Celsius as you go up the chain. So the change in temperature on the Kelvin scale has the same gradations as Celsius, which makes it really nice. So if I want to find out what 100 degrees Celsius is, then that's just 373.15 Kelvin. So you can say that there's still 100, you call them degrees, 100 units of difference between this and this in both cases. So they have the same type of scaling. The Kelvin scale, the Fahrenheit scale does not. The Fahrenheit scale has a very different scaling for each degree than the temperature on the Celsius scale has. Okay. Now, when we do this, and you might wonder, okay, where did that number come from? That's a very obscure number right there. Maybe some of you already know. But the idea is that, and here's a picture of what you can do here. Maybe some of you have done this experiment before. I did this when I was in college, but I went to a very different kind of school where we did just a lot more experiments, I think, than you do at most schools. I'll just ask, have any of you done an experiment in chemistry where you plotted the pressure of a gas versus its temperature? And then tried to use that to work back? Is that an experiment that you all do at this school? Where you plot the pressure of a gas versus its temperature? You're doing it tomorrow. Really, Mustafa? That's cool. So you're literally doing what I'm about to describe tomorrow in class. That's cool. What class is that? Is that Chem 1A or what is that? Chem 4? Okay. I don't know what that's Intro to Chem? Okay, this is exactly where you would do this, okay? So I'm very interested to know, maybe you can even share with us your graphs tomorrow, or maybe next week you can share with us your graph to see if what I'm about to say is true. So what you can do is, I'm going to draw a picture of what's over here, and then we'll go to the picture. So you can take a constant volume gas thermometer, okay? That's this right here. This thermometer works exactly like the thermometers that's described right here, but it uses a gas. So inside of this bulb right here, there's a little spigot, and you can put gas inside of this, and then it will read out up here what the temperature is of the fluid that you've placed in. So in this case, it looks like it's placed into ice water, right? And then you can measure the temperature there. But because there's this spigot right here, it means you can also measure the pressure. In fact, maybe that's measuring pressure. You can't really tell, right? That actually may be measuring pressure. And then you would have to separately measure the temperature, like with a, you could put a thermometer in here, right, and measure temperature. So this either measures pressure or temperature. You would need to measure, I think this is probably pressure, right? That seems reasonable that this is pressure. And you would measure temperature by placing a thermometer into this container right here. The bulb is metal, which means that it's going to be a good conductor, and that means that whatever the temperature of the gas that's contained inside of this vessel is going to be the same as the temperature of the outside part right here if you give it enough time. So if you put a thermometer on the outside here, you can measure temperature, and you can read pressure off of here. Okay. So if you do that, and use different gases, so we're plotting pressure here, and we're plotting temperature right here. What you find is that there's like a straight line. So as you take data points here, so temperature increases this way, and let's say that this, for example, maybe is 0 degrees Celsius, right? You find that for a single gas, you get data points that look like this. And if you do a best fit line, that line will go back to some point. way back here on your temperature axis. Okay, you get the idea of what we're doing here? These would be data points for some gas. Maybe this is oxygen. I don't know. And you notice that all those data points, basically, they all go back to some point, and they intersect with the y-axis right here, or the x-axis right here. You would call this normally like the x-intercept, right? The place where, well, pressure. What is this? What point would this be? I guess I should be really clear. This is 0, 0. If this is 0 degrees Celsius, comma, 0, let's say this is measured in pascals. So the origin is 0, 0, right? So this is clearly some negative temperature over here, right? What's the pressure at this point going to be? Where this line that I've drawn here meets the x-axis. What's the pressure there going to be? It's 0, right? Okay. So at this point, P is equal to 0, and T is equal to something, right? So then you come in here and you say, okay, what happens if I use a different gas? Okay, and I don't know what the relative slopes of these are supposed to look like, but I suspect you're going to do something like this tomorrow, Mr. Mustafa. That suppose you do another gas, okay, and maybe this gas is nitrogen. I don't really know. And then you do your best fit line, right? What you're going to find, very interestingly, this is very shocking. I think it's kind of shocking, is that if you do your best fit line right here, what you're going to find is that for nitrogen, you're going to get a different slope of pressure versus temperature. They won't be the same as the oxygen curve was. But for the nitrogen gas, you come in here and you plot pressure and temperature, pick all these points, and then you draw your best fit line. It will also meet at exactly the same position, the place where it seems as though pressure is equal to 0. And you can continue this process, and you can do it for other types of gases. Do it for hydrogen, carbon dioxide, whatever you want, and you'll find that no matter what gas you choose, as long as your data that you take is good enough, they will all meet at exactly the same point. Okay? Maybe this is CO2. Different gases have different slopes, but they all happen to meet at this exact same point where the pressure is supposed to be 0, theoretically. And if you look at what that temperature is at that point, we can look over at this picture right now. That temperature happens to be exactly negative 273.15 degrees Celsius. Okay? The temperature at this point is exactly equal to 273.15 degrees Celsius with a negative sign in front of it. So this temperature is a special temperature because we believe that at that point, theoretically, the pressure of the gas on its container should be 0. So this temperature, we think, is probably the coldest temperature that is possibly achievable. So we define a temperature of negative 273, this is in Celsius, 0.15 degrees Celsius. We call this absolute 0. We think this is the coldest temperature that is possibly achievable in any setting. Absolute 0. As far as we know, this is the coldest temperature possible. It is not possible to get colder than that. From a classical physics perspective, we think the pressure at that temperature should be equal to 0. But is the pressure actually 0? I don't know. Since that's the absolute lowest temperature you can have, it's very logical to then construct a temperature scale on which that temperature corresponds to 0. So that's what the Kelvin temperature scale is designed to do. It allows us to make it so that our temperature starts from 0, right? And what that means is there's no more negative temperatures when you use the Kelvin scale. So in the Kelvin scale, the temperature in Kelvin is always greater than 0, okay? It will always be greater than 0. And I say always greater than 0 and not greater than equal to because we have never actually achieved this temperature in the lab. We've never actually reached that temperature. We've gotten close. So the lowest that we've gotten, this changes every year, so I don't know what it's going to be now. Maybe it's picokelvin or something like that. The lowest temperatures that we've seen in the labs are temperatures on the order of like nanokelvin or a temperature on the order of picokelvin. Okay, pico would be 10 to the negative 12 kelvins. Nano would obviously, most people know what nano is, right? Nano is negative 9. This would be like 10 to the negative 9 kelvins. And it turns out that as you get to these lower and lower temperatures, it takes way more energy to make the system cooler. Like if I want to go from picokelvin down to like femtokelvin or something, which would be 10 to the negative 15, the energy needed would be monstrous. And it's difficult too. How do we normally make things cold? If I have a soda and I want to make it cold, what do? Several options of what you could do. Throw in the fridge, that's one option. But what if, so the fridge is going to get it down to like 40 degrees Fahrenheit, I think, or I don't know what that is in Kelvin. But what if I want to get it even colder? What do I have to do? The fridge is only going to get it so cold, right? Once it's gotten down to the same temperature as the fridge, what do I need to do to make it even colder? Freezer, okay. And the freezer is only going to get it down to a certain temperature too, right? Maybe it gets it down to like maybe -4 degrees Celsius or something like that. What if I want to go even colder? What am I going to do? Okay, dried ice. Dried ice is pretty cold. You could probably wrap it in dried ice, put it in a cooler. That would make it even colder, yeah. What if I want to go colder than that, though? What in general are we doing here? There you go, Calvin. That's exactly right. You have to keep putting the soda into a cooler environment. Does that make sense to everyone? The only answer is find something colder than the object is, right? Because if I take the soda that's been sitting in dry ice and I put it into set it down on the counter, it'll pretty quickly warm up to the 70 degrees that my house is at, you know? The only way to make things colder, the simplest way, is to just put them into a colder environment. So suppose that I have a system that's at 1 degree Kelvin, and I want to go down and I want to break the record. I want to have the lowest temperature ever achieved in the history of science, right? I want to be able to go out and report that I produced a gas that had a temperature, lower than picokelvins, right? Well, you've got to find something that's colder than it, right? And you're already trying to achieve the lowest possible temperature. So how are you possibly going to find something that's colder than this gas that you're working with, right? You can't. And so you have to come up with other ways to cool things down. And I'll just say that, like, some of the ways they do this is they use lasers that are tuned at certain frequencies, and then they send these waves of light at objects, and given just the right conditions, they can actually remove energy from systems by doing this. This occurs in all kinds of different places within physics, but there's certain types of states of matter that occur at very, very cold temperatures that people want to study. So you all know about probably 4 states of matter, right? Obviously, we've got solids, liquids, gases, but then we've got what's hotter than a gas? What happens when you heat a gas up? What do you get? Some of you that are taking maybe chemistry or something else probably know. You get plasma. And where do we see plasma? Well, plasma is like the sun, pretty much. Plasma is basically the sun. The sun is made of plasma. Plasma is a gas of hot ions as opposed to a gas of hot molecules, okay? The sun is made up of a bunch of hydrogen ions, electrons, helium ions. These things are what make up the plasma itself. Because plasma is made up of ions, it has a lot of electromagnetic properties, such as solar flares, stuff like this, right? That's the hot direction, right? What happens when you go colder, though? Well, it turns out that there are other states of matter when you get colder as well. And when you get really, really, really cold, you can develop something that's called a Bose-Einstein condensate. It's a special state of matter at very, very low temperatures, and it's something that people like to study. It was first discovered or predicted. Maybe it was predicted by Einstein and discovered by, I'm not sure the details of it, but the point is that we call it a Bose-Einstein condensate, or a BEC. It was predicted to exist in the, I want to say the 20s or 30s, and then it was first discovered here in America at the University of Colorado Boulder by a group of scientists in, I think, 1995. So nowadays, people want to study these Bose-Einstein condensates, and one of the ways they study them is by cooling systems down very, very cold to produce them. And again, it's a special state of matter that only occurs at low temperatures. So you gotta learn different ways to get to low temperatures. And like I was saying, one of the ways they do that is by using laser cooling methods that are very creative. So what's the value of this system? Well, the value is now we have a real zero, right? It actually means zero. And the value of that is immense, because now you can start to do mathematics that you couldn't do before. You can start to do mathematics you couldn't do before. And one of the simplest things you can do is say that with a well, you can see it right here on the table. If I have a system and I draw the pressure versus the temperature, and it creates this straight line like this, right? That means that the pressure and the temperature have a constant fixed ratio to one another, right? It means that since there is a temperature of 0 and a pressure of 0 way down at the bottom, that if I pick one pressure, P1, and divide by the pressure at another point, that's going to be the same as the ratio of the temperatures. So this is something that we can do with a Kelvin scale, but we can't do it with a Fahrenheit scale. Only if you measure in Kelvin can you do this. that you can take the ratio of the pressures of a single gas is the same as the ratio of the temperatures. That's pretty powerful. You cannot do this with a negative scale because, for example, if T2, right, was 0 degrees Celsius, yeah, then it completely messes up doing ratios, right? Does that make sense? Like if I have a temperature down here and it's 0 degrees Celsius and I want to compare that to a temperature of 30 degrees Celsius and I want to figure out what the ratio of the pressures will be, well then my right hand side will be 30 over 0. And that just doesn't make any sense. Like, it's undefined, right? But if your temperature can never actually reach absolute 0, then you can totally use this because you'll never have a 0 temperature and you'll never have a 0 pressure because 0 pressure also occurs at absolute 0. All right, does anyone have any questions about this? Should I do an example of what I mean here so that it's clear? Okay. So let's say that we have 1 liter of oxygen that is contained so it can't get out. And let's say that it's at atmospheric pressure, so its pressure P1 is equal to atmospheric pressure, so 1 times 10 to the 5th pascals. And I know that at that temperature, T1, its temperature, let's say, is 70 degrees Celsius. Okay. If I were to increase the pressure, so we'll say here, so we increase pressure to, we'll just double it, 2 times 10 to the 5th pascals. Maybe let's do triple because sometimes I think when I double things I confuse people because it's just too simple. So if we increase the pressure to 3 times 10 to the 5th pascals, what is the temperature going to be? How would you do this? Well, maybe you've got a system like this, okay, and I've got a piston on the top. This kind of thing we're going to see a lot in this class. So I've got a piston up here, and I take my volume, so I have 1 liter of oxygen in here. None of it's going to leak out, okay? And I know that the pressure right now is P1. What we're going to do is we're going to push down on this so that the system basically goes to here. And by pushing down on that, we're definitely going to change the volume. We're also going to change the pressure. And the claim is that if we increase the pressure to 3 times 10 to the 5th pascals, we now want to calculate what the temperature is. All right. And supposedly we could just use an equation like that. But we have to put things in Kelvin. You will have to do this in all your homeworks. If they give you a temperature that's in Celsius or in Fahrenheit, you have to convert, okay? But according to our equation up here, it says that T2 is equal to it would be T1 times P2 over P1, right? So it would be temperature 1, which we have to convert this to Celsius or to Kelvin. So this would become 343.15. Is that right? Kelvin? Is that correct? You just have to add 273.15. Are you answering me, Richard? Okay. So that's our temperature, so we put that in here for T1. Pressure we can leave in pascals, because 0 pascals means no pressure, right? So we don't have to change that. Pascals is already an absolute measure of pressure. Okay, so in the numerator here we have P2, so that's going to be this one. So we have 3 times 10 to the 5th pascals. In the denominator, we have 1 times 10 to the 5th pascals. So our answer for the temperature should increase by a factor of 3. And it should go to 1029.45. Very hot, actually. Which, if we convert that to Celsius, would be equal to about 756 degrees Celsius. Of course, your homework is going to have you switch back and forth between units all the time, so you may have to switch to Kelvin to answer a question and then switch back to Celsius to put the answer in, for example. So just notice, I want you to notice something right here about how this would have worked out. So notice that our first temperature was 70 degrees Celsius, and our final temperature is 756 degrees Celsius. That's about a factor of what, like almost 10 times the temperature increase, right? Did you all agree? It's about 10 times the temperature increase? But that's on a Celsius scale, and saying that the Celsius temperature is 10 times hotter, that doesn't mean anything, because 0 degrees Celsius is negative 273, right? So it's not really 10 times hotter. It's how much hotter? It's 3 times hotter. It's actually only 3 times hotter. So that's kind of the distinction. If I had plugged 70 degrees Celsius in here, I would have got an answer of 210. Would you all agree? If I just take this 70 degrees and I blindly put it into here, my answer would have been 210 degrees, which is way off what the actual answer is. Not to mention, 210 degrees Celsius is not 3 times as hot as 70 degrees Celsius, right? Do you all agree with that statement? 210 degrees Celsius is not nearly, it's not that much of an increase. It's something you can see in your home, right? Well, maybe not, but... Okay, so that's the Kelvin temperature scale. It's really powerful. I will say I came up with this on the fly. There may be some issues here. I mean, the volume is decreasing, and maybe that has an effect on things. The number of molecules is not decreasing, and I do think that this problem is wrong. Like, as in, because the volume actually decreases here, I think you're supposed to use this expression. Okay, so but just keep that in mind. I was just doing this as an example. I don't think this problem is 100% accurate. I think this is what you need to do when the volume changes. Okay, this isn't exactly 100% accurate, but the point is that we can come up with situations where the volume wouldn't change and that this still would work. So I don't know that this is always going to work. Maybe I'm just wrong, but I think this is right. Okay, so what's next? So other ways to measure temperature. Let's wait until we talk about expansion. Let's talk about linear expansion now. That's the next topic. Thermal expansion. This is what I wanted to cover at least this much today, leaving specific heat for next time. Okay. So as we said earlier, most objects, when you heat them up, they tend to expand, okay? And we can categorize exactly how much they expand. Let me pull some of these pictures that we have over here for this up. These. Okay, this is our equation for temperature expansion. This is an example, and this is a picture of something that's related to it, and this is a this is basically all the details we need to have here. So let's look at this picture first. All right, so for moderate temperature changes, delta L is proportional to delta T. What does that mean? So suppose that I have some object, okay, and it has a length, and I call the length of that object L naught, right? and then I increase the temperature of it. Okay, so we add temperature to this. The claim is that its length will change. Okay, so as we go from here to here, we're going to say that the temperature increases. And the idea is that the object is going to expand by a small amount. We are going to call that small amount delta L. Delta L will be this distance here that the object actually expands by in the length direction. It's also going to expand in this direction too, but we're going to talk about that in a second. We're just now going to worry about how much longer does an object get when you add temperature to it. And the idea is that the amount of temperature you add is going to directly be related to the amount of expansion that you get. Objects can cool down as well, but in general, our equation is this equation right here. Let me write it larger so you can see it. It says that the change in length over here of our object is equal to alpha. This is a constant called the coefficient of linear expansion that we're going to look up at a table, multiplied by its initial length and multiplied by the temperature change. That's our definition of thermal expansion that we're going to work with. We're going to use this. This is linear expansion because it's just expanding in a line. We'll also talk about area expansion and volume expansion as well. All right. To understand why this occurs, yeah, maybe I'll try to put these up on the screen too, somehow, some way. Maybe move this one down here. Put these up here. I don't know. It's not really. I guess I don't need. I just need that part, right? Okay. Move these over here. So alpha is a constant that we look up in a table. This is the table right here. You can see what the values are. The units have a dimension of inverse Kelvin or inverse degree Celsius. Something to keep in mind is that when you have a delta T in your equation, okay, alpha is based off the material, Troy, yes. Different materials will have different values. So you can see here that if I compare aluminum and steel, maybe this isn't too surprising. It looks like aluminum has twice as big of a coefficient. What does that mean? Well, according to this equation, if this number is twice as big for aluminum than it is for steel, then for a given temperature change, aluminum would get twice as big as steel would. Is what that means, right? Because steel has a coefficient of 1.2, aluminum has a coefficient of 2.4. So if I subject both of them to a temperature change of like 10 degrees, and they both start off with the same initial, length, then the aluminum will expand twice as much as the steel. But other things like glass doesn't expand nearly as much as steel and aluminum. Quartz doesn't expand nearly as much because there's a factor of 0.04 right here, right? But that's not that surprising, right? It's not super surprising that steel and aluminum, which are metals, and metals we know are malleable. They can be hammered out into sheets, right? You can bend them pretty easily as long as they're thin enough, right? You can take a stainless steel fork. It's pretty easy to bend the tines of a stainless steel fork, right? Because they're malleable, it's probably not that surprising that metals tend to expand more than stuff like quartz. Now, part of the reason why this happens is, I can't remember if this picture is from this chapter, if it's from another chapter, but this picture is a picture kind of related to what a metal might look like in terms of how atoms work in a solid. So inside of a solid, especially in metals, the atoms line up in these type of patterns that are grid-like, or lattice-like, or cube-like, whatever you want to say, where each of these balls is an atom, and each of these springs is a spring that, I want to do something here. Can I line this up on top of it? No, let me move just one of these. I'm just curious. Can I break it out of there? Oh, it won't let me. I want to know if I can take this and place it onto this picture, and then click. Oh, do I have to make it see-through? Can I make it transparent? Anyone that knows anything about this program, let me know. I know you can do this in a lot of other programs where you can lay something on top of it and you can make it transparent. I can't figure out how to do it, and it'll take too much time. So we'll just not do that. Let's get rid of this. What I was trying to say is, inside of metals, the atoms are situated like this. These springs represent kind of a bond between the two metals. And what I wanted to draw here is that this pattern extends, right? There's also going to be an atom here, an atom down here, etc., right? It also extends below. So there's going to be an atom down here as well. But here's the thing. These atoms, if you were to look at the atoms of a solid, they're not sitting still. They're vibrating. They're always vibrating. So any one of these atoms here is vibrating back and forth. It's vibrating up and down, and it's vibrating in and out of the page too. Okay, in 3 different dimensions, right? So it vibrates left and right, it vibrates up and down, and it also vibrates in and out. When you add temperature to a substance, okay, adding temperature to a substance is going to increase the average speed of the molecules because temperature is directly related to kinetic energy. This is something we are not going to derive until much, much later in this class. And I don't really know why, because I have a hard time talking about temperature without talking about kinetic energy. So I'm just going to tell you right now that temperature of an object is going to be proportional to the average kinetic energy of its molecules. And just trust me that at some point in this class, I'll give you an exact relationship for this. And I could write it down now. It's not going to mean much. But the point is that temperature is directly related to the average kinetic energy of molecules of a substance, or atoms, or whatever the smallest part is. Okay? Does that seem reasonable? That as something gets hotter, the molecules are going to start to vibrate faster? Does that seem like a reasonable thing to say? It does, right? I mean, it seems reasonable. Things get hot, they're going to vibrate faster. When I think about it, when I get really cold, my hands, it becomes harder to use your hands when you get really cold, in my experience. That's why you want to wear gloves if you're outside when it's really cold, because then you can still use your hands pretty well. If your hands get like frozen, they kind of almost feel brittle, like it's harder to move them. Okay, so temperature is directly related to the average kinetic energy of the molecules. If you increase temperature, the molecules are going to start moving faster. Now, if the molecules are bound to neighboring molecules, right? Let's look at this molecule here. This molecule is going to have a molecule above it, below it, to the left of it, to the right of it, behind it, but then there's also a molecule sitting out here in front of it, right? So what's going to happen if this molecule starts to vibrate back and forth faster and faster and faster? What's going to happen is that the spacing between the atoms is going to have to actually start to spread out. You're going to need more room for these molecules to vibrate back and forth in and out, etc., or else they'll start hitting each other. So the spacing between the atoms goes up. As a result of the spacing between the atoms go up, the length of the overall macroscopic object is going to increase. That's kind of the idea of what's happening with length expansion. Okay. So I believe that this is very easy to understand if we do problems. So we're going to do a problem, and I'll show you how we actually do this. But one thing I will say is, here's a picture right here. I guess I took off the caption, or I don't know where I got this picture from. But in this picture, what you have is a train track, okay? And what you'll notice if you look at train tracks very closely is that every so often there is a gap in the track, like this, where from top to bottom down here, the tracks aren't actually connected. At least the metal portions of the track are not connected to each other, okay? And obviously a train that's rolling over this long track right here, this little bump isn't really going to matter, right? Same thing as when you drive over a very small bump in your car, sometimes you don't even really feel it. It's almost like as small as a crack or something like that, right? But what these are designed to do is to make it so that when it gets really hot outside, right? When it gets hot outside, supposedly what we're learning here is that the track is going to expand. And if this piece of track expands and this piece of track expands, there's still a little bit of room in between them so that they don't end up touching each other. Because if it gets really, really hot and this piece of track and this piece of track actually touch each other, then the track itself will have to buckle in order to deal with the length expansion, is the idea. So this type of design is placed into different types of engineering places. Maybe you can tell me places where you've seen this before in type of designs of things. Sidewalks being segmented off into smaller sections is one of them. You see cracks, and you don't see cracks, but you see like segments of sidewalks. When you drive under a bridge of a freeway, there's gaps that filled with what look like foam. Are they for the same idea? Yeah, exactly. That's right. When you drive under the bridge of a freeway, you see these gaps. They're exactly the same because every material expands, right? Concrete, cement, asphalt, the metal the roads are made of, any wood that you make the road of, every single thing that you make something out of it's going to expand. And if you make something out of metal, what you see from this table right here, maybe it's not immediately obvious to you, but metals expand way faster than a lot of substances, which means you have to be very careful. So yeah, you're right. I I live in San Pedro, so very commonly I'll drive from San Pedro over to like Long Beach area, and you have to cross over the Vincent Thomas Bridge. And this thing has, basically the bridge is broken up into different sections, and you can see on the bridge that there's gaps between those sections that are designed so that it can expand without causing problems. Okay, so let's see if I've got a problem we can do. We can do this one. How much time do we have? This class ends, is it 55 or 50 after? Can you remind me? How much time do we have exactly? No one knows. All right. Segment of steel railroad track has a length of 30 meters when the temperature is 0 degrees Celsius. So 30 meters is going to be our initial length, okay? What is the length when the temperature is 40 degrees Celsius? Suppose the ends of the rail are rigidly clamped at 0 so that the expansion is prevented. What is the thermal stress set up in the rail if its temperature is raised to 40 degrees Celsius? So I had to grab an equation that you may or may not have seen in your Physics 1A class. It is right here. So we're going to need that for this problem. Tensile stress. I bet this may have been something you did not actually cover in 1A. Probably if you took the class with me, you may have done like one homework problem or something, but it wasn't really something we talked about a lot. Okay, so that's going to be for part B, so we'll just leave that up there. So for part A, what is the length if the temperature is 40 degrees Celsius? Okay, so what we know is that the initial length is 30 meters. Okay, so this is our initial length. We've got our object. It starts off with an initial length of 30 meters. And that's at a temperature of, we'll call it the initial temperature, of 0 degrees Celsius. Okay. What we want to figure out in part A is what is this length when the temperature, we'll call it the final temperature, is equal to 40 degrees Celsius. Our question is, what is the length? Okay. Now, our equation for this says that delta L is equal to alpha L naught times delta T. For us, delta T is going to be equal to the change in temperature. That's going to be T final minus T initial, which is 40 minus 0. We can plug that into here. Alpha, because it says it's a steel railroad track, you always have to do this yourself. You have to go look this up on the internet. Steel has alpha equal to 1.2 times 10 to the negative 5. So I'll just write that down here. Alpha is 1.2 times 10 to the negative 5. And this is in units of degrees Celsius to the negative 1. That's the units. It expands this much per degree Celsius. Okay. So plugging those into our equation here, we'll have delta L is equal to 1.2 times 10 to the negative 5. That's a 1. Degrees Celsius to the negative 1. Multiplied by its initial length. So the bigger it is, the more it's going to expand. That should make sense. Times delta T, which we said was 40 degrees Celsius. Note that if we had done this in Kelvin, delta T would still be the same, even if the final and initial temperatures were different. The change is always, like the change in temperature will be the same, whether it's Kelvin or Celsius. So we can throw all those together. 3 times 4 is 12. 12 times 12 is 144. And we have how many digits here? There's a 10. The 10, that's 10 to the 2, 10 to the negative 3. So this is probably going to be, I don't know, something like this. Is that right? Might be too big. Yeah, 0.0144. I was off by, it's 10 to the negative 2. What is Celsius to the negative 1? That's the unit. That's the unit. I mean, look at the units. They have to cancel out, right? Can you see that this degree Celsius cancels out with this degree Celsius here? It's degree Celsius to the negative 1. It's the unit on delta L. Sorry, it's the unit on alpha. So I actually got 10 to the negative 2 here, which would be about, what is that, 1.4 centimeters? Yeah, it is, right? So that's not the answer, though, right? Because it says, what is its length? So to find its length, we have to actually take L naught plus delta L to get the total new length, which will be, it started off at 30.000 meters. It's now going to have a length of 30. And it's going to change this digit, right? Is that right? Plus 30 equals 30.0144. Sorry, it was one more digit. That's right. And that's going to be in meters. Okay, so just quickly going on to the next part, I'll answer any questions you have after class, because I want to make sure that we get things done. Does the thermal expansion happen evenly to both sides of the rod? It happens all throughout the rod. Yeah, so yes, basically yes. It says B, suppose that the ends of the if you need to go, you can go ahead and go. Obviously, this will be recorded, but we'll just finish up here. We have like a minute. Suppose the ends of the rail are rigidly clamped at 0 degrees Celsius so that expansion is prevented. What is the thermal stress set up in the rail if its temperature is raised to 40 degrees Celsius? So the idea here is that now our same object is going to be prevented from expanding by clamps on either side right here. So we have some kind of thing that's clamped to the earth on both sides right here. We know that the distance between here and here is 30 meters. We know that our temperature is now 40 degrees Celsius, and we want to figure out what the tensile stress in the rod is. So there's two different ways to calculate tensile stress. Tensile stress you either calculate as the force per unit area, because the idea of tensile stress is like you're squeezing something, okay? Or you can do what's called the Young's modulus multiplied by delta L over Li. So the tensile stress in this case, that's what we're going to use. You will see this kind of thing show up on your homework too. In this case, this is equal to the Young's modulus for steel, which we're going to have to go look up, multiplied by delta L over Li. We know what delta L should have been, right? It should have been 0.0144 meters divided by the initial length of our object, which was 30 meters. And now we need to multiply by the Young's modulus of steel, which you can find in your textbook or you can find on the internet, whatever you want to do. I'll just show you where you would find it in the textbook in case that's something that you all actually do. So if we go to bookmarks, and you go back to chapter 11 in your textbook, stress, strain, and elastic moduli right here. They talk about these topics. Again, this may or may not have been something you've seen before, but see there you see tensile stress. And here we see the Young's modulus. This is the thing we need to look up. For steel, it is 20 times 10 to the 10 pascals. So in here, we're going to have 20 times 10 to the 10 pascals. Tensile stress is measured in newtons per meter squared. We multiply this by 0.0144 meters, divide by 30 meters. This is equal to it's going to be a huge number. 96 million pascals. So 9.6 times 10 to the 7 pascals. Or in terms of air pressure, that would be about 960 atmospheres of pressure, which is a huge amount. And this is only approximate. Approximately 960 atmospheres of pressure will be felt inside of that rod, which for certain rods would probably cause them to break. Okay, that's all the time we have for today. So I'll leave you with, you should be able to solve a lot of the homework problems you're going to see in this chapter. The one thing I didn't get to talk about is volume expansion, but I'll leave you with the equation. It is quite simple. It is the same concept. For volume expansion, you do the same thing you do for length expansion. So you have, instead of change in length, you have change in volume. Over here you have the original volume and temperature change. You also need the coefficient of volume expansion, which, as it turns out, is exactly 3 times the coefficient of linear expansion, as you'll see in this picture right here. If I can get it to paste. Yeah, look at aluminum. Aluminum is 2.4. This is the volume expansion on the right, linear expansion on the left. Aluminum has a linear expansion coefficient of 2.4, and it has a solid or volume expansion coefficient of 7.2. So that's a ratio of 3 to 1. Same as brass, 3 to 1. Same as copper, 3 to 1, et cetera, steel, 3 to 1. So in general, what you can say is if you know what alpha is, if you take 3 times alpha, that gives you beta. And that's what we'll stop with. All right, so if you didn't do the lab last week, you're scheduled to do the lab this week. Hopefully I don't need to put up another list. Hopefully everybody knows if they were there last week or not. And everybody else is going to come this week. Okay, so this will be posted soon. I hope you all have a nice day. I'll see you on Wednesday if you're coming on that day.